China recently brought back lunar samples that may contain one of the most talked about materials on the moon. But the real story is what happens if one country reaches the right terrain before the rules about that terrain are fully settled. China's hidden moon resource could shape the next phase of space competition. When people hear the words helium-3 on the moon, they imagine a rare fuel that could power Earth for centuries. But helium-3 is not a working energy solution today. It is not something any country can mine tomorrow. The real importance of helium-3 lies in its strategic value. It is a reason to go to the moon and stay there. And recently, China strengthened that incentive. In June 2024, China's Chang'e site mission returned samples from the far side of the moon. The spacecraft brought back over 1.9 kilograms of lunar soil and rock. That amount may sound small, but the value is in the location. The far side of the moon has never been sampled before. Scientists confirm that some of the basalt in those samples is about 4.2 billion years old. That makes it the oldest precisely dated lunar basalt ever returned to Earth. And these samples help scientists better understand how the moon stores certain rare materials inside its surface layer. One of those materials is helium-3. Now, helium-3 is not new. Scientists have known for decades that tiny amounts exist inside the moon's dusty surface called regolith. Solar wind constantly bombards the moon. Over billions of years, that wind implants small amounts of helium-3 into the lunar soil. But measuring it accurately requires real samples. In 2020, the chang'e mission returned samples that led to the confirmation of a new lunar mineral called chang'e. Inside that mineral, researchers measured the concentration of helium-3 trapped in lunar material. So when Chang'e 6 returned new samples in 2024, scientists gained another opportunity to study how these materials appear across different regions of the moon. That is the geology story. But the strategic story is larger. Before helium-3 becomes meaningful in any real way, several enormous challenges must be solved. First, the material has to be extracted from lunar soil. Helium-3 is not sitting in clean deposits. It is mixed inside the regolith at extremely low concentrations. Mining it would require heating and processing massive amounts of lunar material. Second, the extracted gas would need to be stored and transported safely. Third, it would need to be shipped from the moon back to Earth, which is a huge logistical challenge in itself. And fourth, the entire system would only matter if fusion reactors capable of using helium-3 exist. Right now, those reactors do not exist at a commercial scale. Even experimental fusion systems on Earth are still under development, so helium-3 is not a working industry. It is not even a near-term industry. It is a long-range strategic possibility. Something that might matter 20 or 30 years from now if several difficult technologies eventually succeed. That is the constraint. Helium-3 does not change the world tomorrow, but it still changes how countries think about the moon today. Because if helium-3 ever becomes valuable, the advantage will not go to the country that writes the best legal framework. The advantage may go to the country that already has a physical presence on the relevant terrain. And this is where China's lunar strategy becomes important. In March 2024, China launched a satellite called Chang'e. At first glance, it looks like a simple communications relay. But it is more than that. Chang'e is positioned to enable spacecraft on the far side of the moon to communicate with Earth. That matters because the moon blocks direct radio contact from the far side. Without a relay satellite, sustained operations there are extremely difficult. Chang'e was launched specifically to support 3 missions in sequence: Chang'e 6 and Chang'e 7 and Chang'e 8. That means it is not a one-off science tool, it is part of a planned operational infrastructure. Chang'e 6 has already completed its mission and returned samples. Chang'e 7, planned later in this decade, will explore the lunar South Pole region. That area is important because it contains permanently shadowed craters where water ice may exist. After that, Chang'e 8 is expected to test technologies related to in situ resource use, meaning the ability to use materials directly on the moon. None of these missions alone creates a lunar base, but together they create operational experience and infrastructure. And in long-term space strategy, infrastructure often matters more than individual discoveries, because infrastructure allows future missions to move faster. The Moon's South Pole is one of the most valuable regions on the lunar surface. Water ice could support life support systems and fuel production. Certain areas receive near constant sunlight, making them useful for solar power. And the geology of that region may contain materials that future space industries could eventually use. That is why multiple space programs are targeting it. China is moving toward it through the Chang'e mission sequence. The United States is moving toward it through the Artemis program. But the two strategies look very different. China's approach focuses on physical sequencing, sample return missions, relay infrastructure, surface exploration, technology demonstrations. Each step increases China's ability to operate on the Moon in the future. The United States approach focuses more on institutional frameworks. The Artemis Accords, for example, establish principles for peaceful exploration and resource use. As of early 2026, 61 countries have signed those accords. China is not among them. That means the United States currently holds stronger multilateral legitimacy for lunar governance. But legitimacy and physical access are not the same thing. One builds rules, the other builds presence. Now consider the timeline. NASA's Artemis 3 mission was originally expected to land astronauts on the Moon, but the program has been restructured. Artemis 3 is now planned as a low Earth orbit systems test in 2027. The first crewed lunar landing under Artemis is now targeted for Artemis 4 in 2028. China's timeline looks different. China plans an uncrewed Mengzhou Lanyu rehearsal mission around 2028 to 2029. Then, China has stated that it aims to conduct its first crewed lunar landing around 2030. Those timelines are not decades apart. They are only a few years apart, which means that both programs are moving toward the Moon at roughly the same time. But the type of leverage they are building is different. China is building physical leverage. The United States is building institutional leverage. China is focusing on missions that expand operational presence. The United States is focusing on alliances and governance structures. Both strategies have strengths and risks. The Outer Space Treaty prohibits territorial claims on the Moon, but it contains no enforceable rules governing resource extraction. Here is where the Helium-3 discussion connects back to the strategic picture. Helium-3 might never become an energy resource. Fusion systems that use it might remain experimental. Mining lunar soil at industrial scale might prove to be too expensive. But the possibility alone creates a strategic incentive. Because if Helium-3 ever becomes useful, the country already operating on the Moon will have advantages. They will understand the terrain, they will control landing sites, and they will already have established precedent. In international systems, precedent can matter almost as much as law. If one country operates on the Moon for years before governance rules fully solidify, those operations begin to shape what becomes normal. And once something becomes normal in space operations, reversing it becomes very difficult. So the Helium-3 story is not really about fuel, it is more about positioning. China's lunar missions have produced valuable science. But they also produce something else: experience, infrastructure, and physical precedent. At the same time, the United States is building a broad coalition of partner countries through the Artemis Accords. Those agreements may eventually define how lunar resources are managed, but governance frameworks only matter if they become operational, because space history has shown something important again and again. In many cases, the side that reaches a frontier first shapes the rules that follow, often enough to matter. China's lunar sample findings did not suddenly unlock a new energy source. Helium-3 mining remains a distant possibility, but the discoveries do strengthen the long-term argument for being present on the Moon, because the Moon is becoming a place where infrastructure may eventually exist. And the first actors to establish durable operations could gain advantages that last for decades. So the real question is not whether Helium-3 will power Earth. The real question is this: if physical access to the Moon begins to outpace the legal frameworks designed to govern it, what decision does the United States have to make, and how much time remains.